Welcome to the Midyear Review, and let's get started. So the first thing that we're asking you to do is know the difference between kinematics and dynamics. So if you remember correctly from the beginning of the year, kinematics boils down to how things move, while dynamics describes why things move. And if you can remember the labs that we did, the first lab that we did was we had you walk around and do, sort of look at all the physics devices that we had, and you were describing how those objects move, like speed up, slow down, change direction. And dynamics we did a few months later, where we described why those things move. So if you remember, we talked about simple harmonic motion, and there was tension there, or spring force, or gravity. So that's the main difference between basically the two things that we've been talking about for the past 4 or 5 months. And then we got into to start how all of these things, how we can figure some different things out using equations. So I hope that you've got your equation sheet near you. I'm going to use the equations that we've been using, and let's just get into it. So the first is a one-dimensional problem. A stone is dropped into a deep well and heard to hit the water 4.83 seconds after being dropped. So we're going to figure out if we can determine the depth of the well. And to start off with, we should probably make a chart. VI, VF, A, T, D. And let's plug in what we know. We know that the time is 4.83 seconds. We know the initial velocity of anything that is being dropped is 0. And we want to know the depth of the well, so we're looking for the D. So if you remember that we're dealing with a projectile, you should know that the acceleration is negative 9.8 meters per second squared. And I'm doing a good job labeling all of my numbers here. I'm probably going to get less good at that as we go, just because it takes a lot of time. And I don't want this video to be too much longer than it has to be. But anyway, the final velocity we don't care about. All we know is the initial, the acceleration, time, and displacement. So I'm going to say your best bet for an equation is going to be D equals VIT plus 1/2 AT squared. The VI is going to be 0, so that makes VIT equal to 0. So D is going to end up being 1/2 times negative 9.8 times 4.83 squared. And let's get out the calculator. Half of negative 9.8 is negative 4.9 times 4.83 squared. That should give us a displacement of negative 114.3 meters. And that would make sense because the negative means that the rock has dropped down. I hope you got that, and if you didn't, I hope you understand how to do it. Next question. A dragster accelerates from rest to a speed of 186 meters per second over a distance of 398 meters. Again, VI, VF, A, T, D. In fact, I'm just going to be intelligent and copy this for the rest of the video. So the VI here was rest, so the initial velocity is 0. The final velocity is 186 meters per second over a displacement of 398. We want the acceleration, and we don't care about the time. This is not a projectile, so we can't just plug in 9.8 there. VI, VF, A, and D, I think the equation, again, the best one to use. You could do D equals VIT plus 1/2 AT squared. In fact, I guess we could. I think you could also use VF squared equals VI squared plus 2AD. But, oh wait, we don't have time, so we can't use that. So, VF squared equals VI squared plus 2AD. So 186 squared equals 0 squared plus 2 times a times 398. 186 squared, that is 34,596 meters squared per second squared, equals 2 times 398. That's going to be 796a. So I just multiplied the 2 times 398 and I brought down the a. And that's going to be 0. So now the next step is going to be to divide by 796 to isolate the a. So 34596 divided by 796. That should be an acceleration of 43.46 meters per second squared. Hope you got that, and if you didn't, I hope you understand. Next up, potato gun launches an apple straight up into the air with a hang time of 12 seconds. How high does it go? How fast is it going when it came out of the barrel? So, as you can see, I'm trying to save a little bit of time. This is a little trickier because there's some things that we simply don't know. We know the whole hang time is 12 seconds, so from the time to go up and then the time to come down, that is 12 seconds. But that doesn't really tell us anything because 12 seconds from start to finish means we have a displacement of 0. So if I were us, which I am, we're going to divide this in half. So we're going to look at only half the trip because that will tell us how high the apple went or fell and how fast it was going when it went up and came down. So to figure this out, I'm just going to say, all right, time is 6 seconds. The acceleration is negative 9.8 meters per second squared. We're looking for how high it goes. And that's pretty much all we have. So the question is going to be, if we're going to attack this, which we sort of have to break this up and do it a couple of times, we can treat one part of this problem to figure out how fast it's going. We can find the initial velocity if we look at half of the trip and assume the final velocity is 0. So we can shoot it from here, shoot it up, and then assume it comes to a rest at the top. And that takes 6 seconds. And if we can do that, then we'd know how fast we were going there. Forgetting about the displacement because we'll come back to that. So if there was an equation that's got a VF, a VI, an A, and a T, which I think there is, it's VF equals VI plus AT, we should be able to figure out the initial velocity from the final and the acceleration and the time. So plugging in VI plus negative 9.8 times 6, that would give us 6 times 9.8 negative. That would be 0 equals VI plus a negative 58.8. And then we would add 58.8 to both sides. And that would mean that those cancel out. VI would then be 58.8 meters per second, which goes there. 58.8 meters per second. So that's the first part. The second part is how high does it go? So now we can use these numbers to figure out the displacement. And you can kind of have your pick because we have every single, we have all the variables already. So we should be able to pick pretty much any equation as long as it has a D in it. I'm always partial to D equals VIT plus 1/2 AT squared, but you can use whatever you want. But D equals, for me, 58.8 times 6 seconds plus 1/2 times negative 9.8 times 6 squared. So all of this is going to give us a whole lot of numbers to add together. 58.8 times 6 equals 352.8 plus 1/2 times negative 9.8 times 6 squared. That should be a negative 176.4. So 352.8 minus 176.4. That should be a displacement of positive 176.4 meters. So it went up 176.4 meters. 6 seconds later, it stopped, and then it came down 176.4 meters. Taking 6 seconds both ways to give you a total hang time of 12 seconds. I hope that helped. And if you have questions about it, we can talk about it in class. Couple of quickies. Projectile experiences acceleration as it travels in the horizontal dimension, assuming no additional force or air resistance. That is false. Sorry, I shouldn't have crossed that out. Not true. It is false. Projectiles only experience acceleration in the y dimension, not the x dimension. So that one is true. And as we know, projectiles experience acceleration negative 9.8 meters per second squared, caused by gravity on planet Earth. Next one, Michael Jordan has a vertical leap of 1.29 meters. What's his takeoff speed and his hang time? Total time up and down. This is essentially the same thing as the potato cannon one that we just did, except we're looking at a little bit different, we're looking for some different information. Because we give you the displacement as opposed to asking you to find the displacement. So again, Michael Jordan goes up and then comes back down. We know the displacement is 1.29 meters. So D is going to be 1.29. We don't know the time. We do know the acceleration, which is negative 9.8. Again, I think we should look at half of the trip. So either how fast, so we want to know what his takeoff speed is, so what's his initial velocity. At the top of that 1.29 meters, his final velocity is going to be 0. And we can figure that time out eventually. And once we have that time, well, that's the time up, so we can multiply it by 2 to get the time up and down, which would be the total hang time. I hope that line of thinking makes sense, because I'm just going to do it now. Let's see. So the initial velocity is something. The final velocity is 0. Acceleration 9.8. I think our best bet's going to be VF squared equals VI squared plus 2AD. So 0 squared equals VI squared, which we don't know, plus 2 times negative 9.8 times 1.29. Let's do a little bit of math. 2 times negative 9.8 times 1.29. That should be 0 squared equals VI squared plus negative 25.284. And I don't want this on that side because I want to get VI squared alone. 0 squared is going to be 0 anyway, so we're just going to add 25.284 to both sides. So that will leave us with VI squared equals 25.284. And we can take the square root of 25.284. And that would be a VI of 5.02 meters per second. So 5.02 meters per second. So now that we got that, we should be able to figure out the time. Okay? So I hope that part made sense. Get rid of it. So now I can use any equation that has t in it. And for my money, I think the easiest one to use is going to be VF equals VI plus AT. So 0 equals 5.02 plus negative 9.8 t. I'm going to subtract 5.02 from both sides. So that'll be negative 5.02. Those guys cancel. Equals negative 9.8 t. So 5.02 divided by 9.8. Negative. Sorry, just hold on. Negative 5.02 divided by negative 9.8. Because we're going to divide both sides by negative 9.8. Those cancel. Time is going to be 0.512 seconds. So that's the time to go from 5.02 meters per second to 0 meters per second, which means it's the time it takes him to go up. But we're interested in the time it takes him to go up and come back down, so we're going to multiply this by 2, because we know the time up is the time down, and we should end up with just over 1.02 seconds of hang time equals hang time, even though the time up or the time down is 0.512 seconds. So I hope that sort of makes sense. It's a different number that you put into the chart than the answer to the question is, but what you're dealing with in the chart is only the time up, and what the question is referring to is what is the time up and time down. So you sort of need to pay attention to that. Hope that made sense, and let's go to the next one. Now we're into two-dimensional. So all of a sudden, my chart that I so nicely tried to make now has to have a second piece to it. We're dealing with X and Y dimensions. So a ball is thrown 35 degrees above the horizontal at a speed of 35 meters per second. So there we're dealing with it, 35 meters per second. No air resistance, where's the ball going to land? So ultimately we want to know displacement in the X dimension. The angle is 35 degrees, that's how we're shooting it off. So we need to know this is the VI total, which if we remember from my class at least, where do we put the 35? I hope you say nowhere, because 35 is just going to be used to get us the X initial velocity and the Y initial velocity. So to get the X, it is 35 cosine 35 degrees, and the Y is going to be 35 sine 35 degrees, and these two things will go in the XY dimension, or the XY chart. 35 cosine 35, 35 sine 35. So the X dimension is going to be 28.67 meters per second, and the Y is going to be 20.07 meters per second. 20, not 26. So we're done with our triangle now. We know a couple of things because I hope we paid attention in class. Do things speed up or slow down in the X dimension if they are projectiles? No, therefore the acceleration is 0. And if we start at 28.67 meters per second in the X and we don't speed up or slow down, we're going to end at 28.67 meters per second in the X. And if we go up with 20.07 meters per second, we are also going to come down at the end 20.07 meters per second, because the acceleration is negative 9.8 meters per second squared. So I hope this is stuff that we remember. So to show you graphically, we're going to make a nice parabola. We know we're going up 20.07 meters per second, that we're also coming down 20.07 meters per second. We're looking for this displacement in the X, which is why I've got the box there. The thing we have to figure out is time, because time up and down is the same as time all the way across. So if I were you, I would be looking for an equation that has a VI, a VF, and a T in it, and we will use all of our information for the Y half of this to figure out what's going on in the X. For my money, again, I think VF equals VI plus AT. It's probably your easiest bet. VF is negative 20. I'm just going to round it to negative 20. Equals positive 20 plus negative 9.8 T. Negative 20 minus 20 is going to be, so we're going to subtract 20 from both sides. Those are going to go away. Negative 20 minus 20 is negative 40. Don't make that 0. I've seen it happen too many times. It was negative 9.8 T. Divide both sides by negative 9.8. Boom, boom. Time will be negative 40 over negative 9.8, which should be about 4. Negative 40 divided by negative 9.8, 4.08. So time, I'm going to round to 4 seconds. I don't think Mr. Tachi or I are going to go crazy. if you take that rounding liberty. But I'm going to say, all right, so time up and down is 4 seconds. That means it also gets to go across at for 4 seconds. So when we have, we're going to look now at the x dimension, and the equation we can use with the x dimension, because we are not accelerating, is v equals d over t. Our velocity is 28.67 equals displacement, which is what we're looking for, over time, which is 4. 4 times 28.67 times 28.67 equals 114, call it 0.7 meters. So that's how far away it'll land. I hope that made sense. I hope you remember this, because this is something that you will see pretty often on the Midyear. Using your Y stuff to get your X stuff is what we like to do. And you'll see that in the next couple of questions too. One more thing. In my class, we always call these launch problems, but we didn't learn this type of problem first. We used a cliff problem, which is what's next. So 2 dimensions again. I'm going to put my chart. But again, we're dealing with 2 dimensions now, so let's get an X and a Y. And here we go. The Grand Canyon at its deepest point is 800 meters deep. If I were to drop a rock into this part of the canyon, how long would it take to hit the bottom? B, if I threw the same rock at initial velocity of 20 meters per second in the X dimension, how far away would land from the X dimension, or in the X dimension from where I was standing? So this is another instance. It's a cliff problem, and I'm going to do it just in the 2-dimensional way, but the whole point of this is to show you that the 1-dimensional time and the 2-dimensional time is exactly the same. So let's just do it. If you remember, there's my cliff, here's the rock, it's going to go like that. We know the displacement is negative 800 meters in the Y dimension. We're going to look for how far it goes away in the X dimension. We're also going to try and figure out the time for it to fall. And we know the acceleration of the X is 0 and the Y is negative 9.8. This is going to answer question A. All right, if I drop it into the deepest part of the canyon, how long will it take to hit the bottom? To continue this, the X initial velocity is, according to the problem, 20 meters per second. And if in any cliff problem, the Y initial velocity is 0. So that's something that we have to remember. I hope you remember. The X final velocity is also going to be 20, because things don't speed up or slow down in the X dimension for projectiles. And honestly, I don't care about how fast it's going as a final velocity in the Y dimension. So there's a picture. Let's start playing with some numbers and some equations. So to start this off, I'm going to recommend that we look for an equation that we can find the time. So we can't really do much with the X, but we can do it with the Y. An initial velocity, an acceleration, a time, and a displacement. I think our best bet's going to be D equals VIT plus 1/2 AT squared. So negative 800 equals 0 times t plus 1/2 negative 9.8 times t squared. 0 times t is just going to be 0, which I'm not even going to bother to rewrite. So negative 800 equals half of negative 9.8 is negative 4.9 t squared. And now we're going to divide both sides by negative 4.9. So that's easy. T squared is going to equal negative 800 divided by negative 4.9. So that should be a t squared of 163.26 meters per second squared. But we're not interested in t squared, we're interested in t. So we're going to take the square root of 163.26. And we should get a time of about 12.7 seconds. 12.7 seconds. I hope that makes sense. Now that I have that, that's the answer to A. How long does it take to either drop or throw this thing horizontally? 12.7 seconds. The next part of the question is how far away is it going to land? Well, now we're dealing with something that doesn't accelerate in the x dimension. So we can use v equals d over t for anything in the x dimension. V is 20. Displacement is what we're looking for. And time is 12.7 seconds. Cross multiply. So 12.7 times 20 is going to be 254. And d times the understood 1, d will be 254 meters. 254 meters away. I hope that makes sense. I hope you remember that. And again, if you don't remember it, please feel free to ask about it in class on Thursday or Friday. Marble is rolled off the desk. It lands half a meter away from the edge of the desk, and the desk is 0.7 meters high. How fast was the marble traveling when it was rolling? This should sound like X marks the spot. So we did a lab about this. Let's get this, we'll do this, bring this there. Again, we're dealing in 2 dimensions, so let's get an X and a Y, and let's figure out what we know. We know the marble lands 0.5 meters away. The desk is 0.7 meters high. Okay, so that means the marble dropped 0.7 meters. I don't know time. I know the acceleration in the x is 0. I know the acceleration in the y is negative 9.8. I know the initial velocity in the y is 0 because it rolled off the desk. And we're looking for the initial velocity in the x, which is, this is going to be kind of interesting. Again, I need to find the time. So if I can find the time in the y, that's also the time in the x, and then I can use the distance and the time to figure out the velocity. So an equation, a vi, an a, a t, and a d, I think the best bet is going to be d equals vit plus 1/2 at squared, negative 0.7. This is all the y stuff, by the way, okay? Equals 0 t in the y plus 1/2 negative 9.8 t in the y squared, but t in the y is the same as t in the x. So that's going to be 0. Negative 0.7 equals half of negative 9.8 is negative 4.9 t squared. We can divide both sides by negative 4.9. Those go away. Negative 0.7 divided by negative 4.9. 0.7, 4.9. That should give us a t squared of 0.142 seconds. And then we want the square root of that, because we don't want t squared, we want t. T should be 0.37 seconds. So that is what can go here. I hope that makes sense. And now from there, I can go ahead and look at what's happening in the x dimension. How fast was this thing going? So I know it traveled 0.5 meters in 0.37 seconds because that's how long it took to fall off the desk. And anything that we're dealing with in the x dimension doesn't accelerate, so we can use this equation, v equals d over t. We can plug some stuff in. v equals 0.5 meters in the x over 0.37 seconds. So 0.5 divided by 0.37 should be, not that because I have big fingers, 0.5 divided by 0.37, 1.35 meters per second. And I hope I haven't screwed any of this up. 1.35 meters per second. Okay, I hope that made sense. And if it didn't, we can talk about it in class. This looks like, if I remember correctly, yep, the last kinematics problem. So hooray, we're almost done with this chart. I know you can't wait. But we are dealing again with 2 dimensions. Let us go ahead and make an x and a y. Let's see here. We got a projectile that is launched 40 degrees above the horizontal, assuming it lands 6 seconds after it's fired. So my time, we give us the time. How fast is it traveling when it was fired? So we want to know what this I don't even want to put an X there because I don't want to confuse anybody and think that we're looking for an X initial velocity. We want to know how fast it was traveling when it was fired. So what was the exit velocity? So we want to know what that hypotenuse is. To do that, we need to know what that X or that Y is, because once we have either the X or the Y, then we can figure out, and we can use the 40 degrees to figure out what the hypotenuse is. Okay, so from there, let's see. Potato can is fired 40 degrees above the horizontal, assuming it lands 6 seconds after it was fired. How fast is it traveling when it was fired? Well, this is going to be a little bit tricky, isn't it? If I was us, I would ignore the 6 seconds. And I'll tell you why. I don't know. I know the displacement after 6 seconds in the y dimension is 0, and there's nothing in here to tell me how far it went in those 6 seconds. But I do know that after 3 seconds, it completed half of its journey, which is to say, I know it took 3 seconds to go up. And I hope that makes sense. And after 3 seconds going up, I know the final velocity was 0, and I know the acceleration was negative 9.8. And here I know the acceleration is 0. Now, why is this important? Because I can use this 3 seconds, this negative 9.8, and this 0 to figure out my initial velocity, which is that. And if I have the y dimension and the angle, I can figure out the hypotenuse. I really hope you follow the logic. Okay? So now, which equation can I use? A VI, a VF, an A, and a T. VF equals VI plus AT. So 0 in the y equals something in the y plus negative 9.8 times 3. Negative 9.8 times 3 should be negative 29.4. So 0 equals VI plus negative 29.4. I'm going to add 29.4 to both sides. So my VI in the y is 29.4. And if we know enough about trig, that's all I need here. I don't even need this anymore. So I have, this is my right triangle, 29.4 meters per second. I'm looking for that, and I have an angle of 40 degrees. Make sure, and I didn't say this at the onset, to be sure that you're in degree mode. So this is my hypotenuse, this is my opposite side, and I have an angle. Last time I checked, we can use sine when we're dealing with opposites and hypotenuses. Sine of 40 degrees equals the opposite, 29.4, over the hypotenuse. Sine 40 is 0.64. That equals 29.4 over h. To give myself some more room here. So the next step is not going to be, just divide 0.64 by 29.4. Don't do that. Multiply both sides by h, because we have to get the h by itself. So now h times 0.64 equals 29.4. Now we're going to divide both sides by 0.64. Divided by 0.64. That would mean that my hypotenuse is 45.93 meters per second, almost 46 meters per second. And that is how you answer that question. So how fast is that? 49.93 meters per second. Not this. We actually didn't even use the x. We just used the y and some trig to figure out the hypotenuse. I really hope that made sense, and if it didn't, we can talk about it in class. But this is a very difficult problem because we don't tell you anything other than 6 seconds. So from there you have to realize, if I know it's 6 seconds up and down, I know it's 3 seconds up and 3 seconds down. And if you know what's happening with the up or the down, you can figure out the y velocities. All right, so 4 fundamental forces of the universe. I'm going to give you a spoiler alert. Know what they are and know what they do. Be able to give examples of them, okay? So the first that we understood was gravity. The second that we tried to figure out was electromagnetism. The third was the strong nuclear. And the fourth was the weak nuclear. Okay, so gravity makes stuff fall. Electromagnetism is for chemistry or compasses, etc. The strong nuclear makes big booms. Nuclear weapons, WAPONS. And the weak nuclear is responsible for radiation after a nuclear blast. Okay, so I hope that refreshed your memory. That was the fun video with the dude walking through the wall. An applied force of 50 newtons is used to accelerate an object to the right across a frictional table. The object encounters 10 newtons of friction. Use diagram to determine the normal force, net force, mass, acceleration of the object, nuclear area resistance. All right, so we know we're sitting on a table, so gravity and normal force have to both be 80 newtons. I know 50 and 10 are my forces going across. So we know F net, which equals ma, but it also equals what happens when you add all these forces. 80 and 80 cancel out, so your net force is going to be positive 40 newtons. And in order to figure out what the acceleration is, we need to use the equation F net equals ma, but I don't know what the mass is. But I do know the gravitational force is 80 newtons, and I know 80 must be equal to the mass times the gravity. So 80 equals mass times negative 9.8. Actually, it's negative 80 because we're doing math, and we have to remember that it's negative. So 80 divided by 9.8 should be 8.16 kilograms. And if the F net is 40, equals 8.16 kigs times the acceleration, 40 divided by 8.16, that should be 4.9 meters per second squared. I hope that made sense. It's just a little bit of figuring this out. Next. Now we're dealing with a 5 kilogram object, and it is going to the right, encountering a force of friction which slows it down. Coefficient between the object and the surface is 0.1. Determine the force of gravity, normal force, force of friction, net force, acceleration, neglect area resistance. All right. So we know the mass on this thing is 5. So to figure out the gravitational force, it's going to be 5 times 9.8, which is 49 newtons. Down, negative. If it's on a table, again, the normal force must also be 49 newtons, but that's going to be going up because it's positive. And FF equals mu times the normal force. Well, mu is 0.1. The normal force we just figured out is 49. So the force of friction must be 4.9 going in the left direction, so that's why we're going to put a negative there. So 4.9. So that's all we can do there. Now we know the mass is 5. We can figure out the acceleration and the net force. Well, the 49 and the negative 49 cancel out. So the force of friction is really the only thing that's causing this thing to slow down, which is to say the net force is negative 4.9 meters per second squared. And F net equals ma. The net force is negative 4.9. The mass is 5. The acceleration is what we got to figure out. Negative 4.9 divided by 5. That means the acceleration is negative 0.98 meters per second squared. I hope that made sense. More coffee. And we can move on to the next one. 16. A 5 kg box is hanging from the ceiling as shown. There is an applied force applied to the right of 20 newtons. please draw a free body diagram with magnitude and direction of all the forces. So we have a 20 Newton to the right. We have this tension going that way, which I don't know, but that is FA. And there should be gravity. And it's a 5 kg box, so how big is 5 kilograms in terms of gravitational force? 5 times 9.8 should be 49 newtons. So there's a free body diagram, but I have to figure out how big the tension is. I know that I got 3 forces: tension, applied, and gravity. So the applied force only works in the x, not the y. So that's going to be 20 newtons. Gravity doesn't work in the x, but it does work negative 49 in the y. So let's see here. If I want everything to add up to 0 here, 20 plus 0 plus negative 20 in the x, and positive 49 in the y, that'll all add up to 0. So that means my tension has to have an x component that is 20 to the left and 49 up. And geez, that looks like 2/3 of a right triangle, doesn't it? 20 squared plus 49 squared. We can do some Pythagorean theorem. 2801, but that's not really what I want. I want the square root of that. That means my tension is going to be 52.9 newtons. A squared, B squared, C squared. That's really all there is to it. And there's your breakdown of the forces and who's doing what in the x and y, and this is what you end up with. So this is what your free body diagram actually truly looks like, because you don't really need those things. You just need the 3 forces: the tension, the applied, and the gravity. Hope that made sense. This one is actually very, very simple. Brian is walking through the school cafeteria, doesn't realize the person in front of him just spilled his carton of chocolate milk. Brian weighs 420 newtons, steps in the milk. Coefficient of friction between him is suddenly reduced to 0.04. What's the force of friction between him and the floor? Well, FF equals mu times the normal force. Mu is now 0.04. The normal force, well, if he weighs 420 newtons, that means the floor must be pushing up with him with 420 newtons. So 0.04 times 420 should be a force of friction of 16.8 newtons. And he slips. While redecorating her apartment, Kitty slowly pushes an 82 kilogram tiny cabinet across the wooden dining room floor, which resists sliding with a force of 320 newtons. What's the coefficient of friction? So now we're looking for mu. FF equals mu times the normal force. Force of friction is 320. Mu is what we're looking for, and normal force. Well, normal force isn't 82, but we know the mass is 82 kgs, so that means Fg and Fn. Fg must be 82 times 9.8, which is 803.6 down, which means the normal force must be 803.6 up. So mu times 803.6. Got it. So now to figure out mu, we're going to divide both sides by 803.6. 320 over 803.6 equals mu, and that would mean 320 divided by 803.6, 0.39. There's your mu. This guy is trying to make her 70 kilogram St. Bernard go out the back door. Dog uses it to walk. Coefficient of friction between the dog and the floor is 0.5. How hard must the guy push the dog in order to get it to go with constant speed? So again, we got a 70 kilogram St. Bernard. Forces Fn, Fg. And we need the applied force to be exactly equal to the kinetic friction. So the gravitational force is 70 times 9.8, 686. That means normal force is 686. And she has to push just as hard as kinetic friction. So FFK equals mu Fn. Good thing I made this free body diagram so I know how big the normal force is. Mu is 0.5 times 686. So that means the friction is 343. So that means she has to push 343 to keep this dog moving at a constant speed. She would have to push it harder to get it to move, but in order to keep it moving at a constant speed, it would just be 343 newtons. Deer jumps out in front of my car as I am traveling really fast. I just want to see how long this video is so far. 45 minutes. All right, we're almost done, so that's good. Deer jumps out in front of my car as I'm traveling 25 meters per second. I jam on my brakes and lock them with the mu between the tires and the ground is 3.6. The mass of my car is 1,250 kilograms, and there's 50 meters between my car and the deer. Will I or will I not stop before the deer? Okay. So this has two pieces to it. First piece it has is this whole forces thing. And then the second piece is the kinematics. So I'm going to set up my kinematics chart first and then sort of tell you what we have to figure out. My initial velocity is 25. My final velocity, we hope, is 0. I know that there's 50 meters between me and the deer, but I want to know how far it takes me to stop. And what's going to stop me? An acceleration that I have to figure out. Where's that acceleration going to come from? The forces, specifically the force of friction, which equals the net force, which we'll get to. So here's the free body diagram of my car. I've got a 1,250 kilogram car, which means it's got Fg to it, it's got Fn to it, and it's going to have friction to it. Guess what the normal force and gravity are going to do? Cancel out. So whatever these two are, it doesn't matter. The FF is what I need to figure out because that's going to equal my net force, which is equal to my MA, which means I can figure out the acceleration and figure out how far it takes me to stop. I hope that line of thinking makes sense. So anyway, gravity is going to be 1250 times 9.8. 1250 times 9.8. 12,250, 250. And the normal force will also be 12,250. And the force of friction is going to be FF equals mu times the normal force, which is 12,250. But the mu is 3.6, so let's multiply that by 3.6. 44,100. Oh boy, FF equals 44,100 newtons. That is a lot of newtons. That equals F net, which equals MA. So 44,100 newtons I hope that makes sense. So 44,100 equals the mass, which is 1250, times the acceleration. So let's divide that by 1250. That should be an acceleration of 35.28 meters per second squared, which can go there. But here's the beauty of it. Speed up or slow down. What does that 35.28 do? That should slow me down, which is going to make this a negative. Again, we're doing the math now. So, which equation do we have, VI, VF, A, and D, that can figure out the D? I would say VF squared equals VI squared plus 2AD. I hope this makes sense before we get into this. So 0 equals 25 squared plus 2 times negative 35.28 times D. I've done this enough that 25 squared is 625 plus about 70.6 negative 35.28 times 2. Yeah, 70.56, not bad, times d equals 0. Let's subtract 625 from both sides. So negative 625 equals negative 70.56 times d. Let's divide both sides by negative 70.56. Boom, boom. 625 negative divided by 70.56. That is a 70, not a 2. 70.56 negative equals a displacement of 8.85 meters away. That means I stop in 8.85 meters, and Bambi is still another, 50 meters away to start. 8.85, Bambi's still like 41 meters away. This is good tires. That's what that really means. All right, so do I or do I not have a bad hood ornament? No, hit deer. Okay, sound good? Let's go to the next one. We're almost there. A fisherman, and then bowling balls, and then grass. This is good. Fisherman gets into an elevator with a 2 kilogram halibut hanging from a fishing line. The elevator begins to accelerate up with a acceleration of something. The fisherman's line has a maximum tension of 20 newtons. Will it snap? So we need to draw a free body diagram of this fishy. Okay, 2 kilogram halibut has a FG and an FT. Okay, so the FG of 2 kilograms, 9.8 times is negative 19.6 newtons. Now, the whole thing, F net, equals MA. The whole 2 kilograms is moving up, accelerating at 2.5 meters per second squared. So that means my net force has to be 2 times 2.5, which is positive 5 newtons. I hope that makes sense. So that means the tension and the gravity have to add up to positive 5 newtons, which means my tension has to be 5 newtons more than 19.6 newtons. Does that make sense? So F net equals Fg plus Ft, which equals 5 newtons. Okay, so the F net is coming from the gravity plus the tension. Well, I already know the gravity, and that is negative 19.6. So the tension has to be added to that negative 19.6 to come up with 5 newtons. Add 19.6 to both sides. 19.6. That means we are going to have a tension that needs to be 24.6 newtons. Now, what is the maximum tension we can handle? 20 newtons. That means my fishy is not like that. My fishy is on the floor. Like that. That fishy. On the elevator. Okay? Hope that makes sense. Was the final velocity of a bowling ball that has a mass of 7 kgs after it's traveled 30 meters down the bowling alley? Its total initial velocity is 17 meters per second, and the mu is 0.3. This is another one of those forces and kinematics. So the VI, VF, A, T, D, give you a hint, we need to figure out the acceleration, and then we need to figure out the final velocity. We know the initial velocity is 17, and we are looking at the displacement of 30. So we need the acceleration and the final velocity. How are we going to do it? Forces. In this case, again, we've got a 7 kilogram bowling ball, which is dealing with essentially three forces, Fg, Fn, and FFk, kinetic friction. The gravitational force is going to be 7 times 9.8. It's going to be 68.6. Normal force will also be 68.6. And that means the friction is going to be FF equals mu times the normal force. We have a mu of 0.03. 0.03 times 68.6 times 0.0. So that would be, the friction is 2 newtons, 2.058. I'm rounding it down. And the net force, which equals friction, gives me mass times acceleration. So 2 newtons equals 7a. 2 divided by 7 give us an acceleration of negative 0.28 meters per second squared. I'm saying negative because it is slowing down. Okay, you throw the bowling ball in front of you, the acceleration must be negative if it's going to slow down. So my acceleration, not 28, that would be a very sticky bowling ball, 0.28. 0.28 negative. So VI, VF, AD, I'm going to say VF squared equals VI squared plus 2AD. VF squared is what we're looking for. VI squared is 17 squared plus 2 times negative 0.28 times 30. 17 squared, let's just do some math. VF squared equals 289 times, plus 2 times negative 0.28 times 30. 289 plus negative 16.8. 289 minus 16.8. So that would be a VF squared of 272.2. But I don't want VF squared, I want VF. So VF is going to be 16.49. So basically what happens is, and this, I've seen so many people mess this up, they forget that it's a negative acceleration. So it started at 17, it ended at 16 and a half or so it slowed down. So many times people forget that it's negative, they leave this as a positive 0.28, and they say, well, we rolled the bowling ball, it experienced friction, and it went faster from 17 to 17.4, 5.1 or something like that. So don't get caught in that trap. It's a negative acceleration, so it slows down. You should end up with a final velocity that's slower than your initial. All right, so that's all the tough stuff. Now the fun stuff. We have here a position versus time graph. Let's talk about what's happening. All right, you would write this down, but let's just get into it. Constant positive velocity, that's a plus. So that's part 1. Part 2 would be rest. Part 3 would be constant negative velocity. Part 4 would be rest. Part 5 would be constant positive velocity. Point 6 would be constant negative velocity. Point 7 is rest. Again, this is because it's position versus time graph. So you are going, if you were going to walk this with the vernier lab sensors, you'd be walking away, then you'd be stopping, then you'd be walking towards, then you'd stop, then you'd walk away, then you'd walk towards, then you'd stop again. Okay? And if we remember correctly, this doesn't have any parabolas, but if we ever did see a parabola, we would have an accelerated motion. So, next one. 24. Oh, look, how convenient. Parabolas. Position versus time again. So, part 1 would be at rest. Part 2 would be constant negative velocity. Part 3, a parabola opening up, constant positive acceleration. Part 4 would be rest. Part 5 would be constant negative velocity. And part 6 would be rest again. And then for our last one, this is a velocity versus time chart. So now we're dealing with anything that is on the 0 line is at rest. That's a big difference. Anything that is sloped is an acceleration, and anything that is flat would be constant velocity. Okay? So part 1 would be on the 0, so it's at rest, and it's constant velocity. So however long this is, 1 second or 5 seconds or whatever, you're not moving. 2, you are positively accelerating, okay? And you are moving in the positive direction. Positive acceleration, positive velocity. Then you are moving negative acceleration, but still in the positive direction. Okay, you're just getting slower. Then at 4, you stop. Okay, velocity is 0. At 5, you have a negative acceleration and a negative velocity. That means you're going faster backwards. And then you have a positive acceleration but still a negative velocity. That means you're slowing down. And then at 7, you are stopped again. At 8, you have a positive acceleration, positive velocity, so you're speeding up. At 9, you have a constant positive velocity, so you're not going faster or slower during this whole time. And then real quick, at 10, you jam on the brakes and you stop. So that's it. I hope I refreshed some of your memories for the midterm. This is pretty much 1 or 2 of every type of problem we've done for the first semester, and I hope it helped. Alrighty, I will see you in class.